Anybody please confirm if I am audible and visible? The slides. Just one of you confirm. Devlina, can you hear me?
Yes, sir, you're audible.
Yeah, thank you.
And flip-flops are being shown.
Yes, thank you. So today we'll cover latches and flip-flops. You have already studied finite state machines, and you have seen in the Huffman representation is that the most important component of a finite state machine is the memory. So the memory is implemented using the latches, of which flip-flops are a special type. It's kind of a synchronous latch. So we have already used the D flip-flop, assuming it's in input-output mapping. We'll study some more type of flip-flops and see that how they can be used to design sequential machines. So the basic uh, memory element, we can say, which stores just one bit of information, in the sense that you have two voltage levels, you have two states, two voltage levels, one denoted as 0 and another denoted as 1, and the memory element is supposed to store or hold any one of these voltage levels as desired, say either the 0 level or the 1 level. It has to hold or store for some amount of time. So the most fundamental circuit is the following, which is kind of a two NOT gates connected end to end. So this is the yes, two NOT gates connected end to end in a feedback loop. Okay, so what happens? Suppose an high voltage or a one state is given as input to this NOT gate. So this will be 0 and this will be 1 again, and this 1 will again be the input to the first NOT gate. So and the reverse is also true. So see, if this is 0, this becomes 1 and this becomes 0, and that is fed back. So if somehow the input or so if we look at the voltage value here, if we look at the voltage value, if we somehow measure the voltage value as the output of the second NOT gate, and that we call as a variable Q, this Q is kind of hold or stored for a time. So if somehow the input of the NOT gate is set to 1, then Q is 1 forever. It always stays at 1. Similarly, it is set to 0. Q always stays to 0. So Q is the state of the memory. So if we call these two NOT gates together as a memory element, 1 bit memory element, Q is the bit. Q is the value of the that is stored. So there is, you can also look at it like this. So suppose I plot in this, say it will look like this. If we take a single NOT gate and if we take the input, let's call it as Vi, and you take it the output, you call it as Vo. So suppose initially the NOT gate's input is 0. And what will happen is that I start applying an input voltage. So as the input voltage changes to a high value, what happens? The output voltage will slowly change and attain a high value. Rather, the curve will look like this. So if you, as you keep on increasing the input voltage, the output will keep on increasing. It's a NOT gate, so the sorry, it should be the other way around. It should be the other way around. So as we increase the input voltage, if initially it was high, it will go down and come to a lower value. Okay. The point to be noted is that it's not an abrupt step function kind of change. There is a slow change because of the nature of the circuit, nature of the device that is used to build the circuit. And when you are connecting so let's say this is the input output for the first NOT gate. And what we are doing, the output of the first NOT gate is the input of the second NOT gate. So you will, thus the axes are reversed. So you will get something like this for the second NOT gate. Okay, and this high value is kind of a stable state. We have already seen if it is in 1, it will continue to stay at 1. Similarly, if it is as 0, it will continue to stay at 0. So these two are kind of stable states. Okay, and this one in between is called a metastable state, in the sense that once the value is somewhere there, it will try to move out to one of these stable states, right? So but the thing is that we have two stable states. It's a bistable circuit. We have two stable states, and whenever it is out of one of the stable states, it will try to go back to one of the stable states. And also important thing to note is that if you somehow give the input as one of the stable states, it will continue to, the Q value will continue to stay in that stable state. Okay, so this is a very nice memory element that we can have, but the problem is that we would not, our stable state, one of these two stable states, we would like to control at our will. So some amount of time we want Q to be, depending on our requirement, we want Q to be at 1, at some other time we want Q to be at 0. So we need some way of controlling this 1 and 0. So we need some way of being in a stable state, then moving away from stable state to the other stable state, and then if necessary moving away from that stable state back to the stable state. We need to move among those two stable states. And once you move there, so two things are required. One is once you are in a stable state, still there is no further movement. We want to stay in the stable state. That means we want to memorize. And we should be able to switch between these two stable states. We should be able to, by means of external input, whenever some external, some particular type of external or desired type of external inputs come, we should be able to switch among these stable states. And that gives us all the things that we need from a memory element. In memory element, we need two things. We need to either set the memory values or write to the memory value 1 or a 0. And once you have written to the memory value, the memory should hold it. Still, there is further command to overwrite what has been written. Okay, so let's see how we can have this external input to write to this memory element, to update the memory element to either 1 or 0. Again, everything is single bit so far. All right, so what we will do is the following. We'll replace this NOT gate by, let's say, a NOR gate. We'll replace this by a 2-input NOR gate. Okay, and one of the input is as before, this feedback loop. The other input we'll call as external input. Let's call this as set input and a reset input. Okay, a set input and a reset input. So I replace the NOT gate by a NOR gate, 2-input NOR gate. One of the inputs stays this feedback, this connection, and the other input, one of the NOR gate we call as a set input, the other NOR gate we call as a reset input. And what we hope is that, and this Q, the output of the NOR gate, will, in fact, you can denote this as Q bar. because this will be negative of Q. There's an let's call it negative as Q. Okay, we'll see why it is negative of Q. So we have two outputs, Q and Q bar, output of each of the NOR gates, and the second input of each of these NOR gates we call S and R. Let us write down this NOR gate circuit in a slightly different manner. The same circuit, I am drawing it in a different manner. Okay, so this is one of the input of the NOR gate. This is Q, one of the output of the NOR gate, Q bar, the output of the other NOR gate. Now you see the output of one NOR gate is the input of the second NOR gate. So this is the output of the. Similarly, the output of the second NOR gate is the input of the first NOR gate. One of the input of the second NOR gate. So this and the circuit I drawn below is just another form. Side by side, I am drawing the NOR gates. It's the same circuit. And there is a cross coupling. That means you have two NOR gates. The output of one is the input of the other, and vice versa. Okay, and there are the NOR gate has two inputs. The other input I call as set S and R, set and reset, and output I call as Q and Q bar. So this circuit is called a latch. It's called a latch because of this cross connection kind of thing. Now let us see what happens. Suppose okay, I'll draw the circuit on main details. Okay, we'll see that it is actually easy to analyze. We'll soon analyze that when the value of S is 1 and R is 0, Q becomes 1. The value of 1 is written to Q. And the other way around, when the value of R is 1 and S is 0, the value of 0 is written to Q. Okay. And if S and R are 0 and 0 both, it's a hold condition. That means no Q is not updated, but Q is the previous value of Q. It is the previous value of Q. Okay, so if you keep on, as long as you set your S and R to 0 and 0, Q will hold. Q will memorize what has been written. It will just store the memory. And moment S becomes R, Q is overwritten by 1. Moment R is set to 1, Q is overwritten by 0. So perfect memory element. So this is called a latch, rather a SR latch. Okay, so you can also easily see that. Let's see. I have a kind of a small animation kind of thing. You can see. So if R is set to 1, you see. Okay, this becoming rather a uncontrolled sequential action that's going on. But anyway, let's. I think I cannot control it anyway. So when R is set to 1, you will see that this is the. So when R is 1, this whatever is the value of Q, it's a NOR gate. So when R is 1, the output is anyway 0. So this becomes 0, irrespective of what this other input is. So when R is 1, it's a NOR gate. So the output is 0. If the output is 0, and since this is also a NOR gate, the output will be 1. So no, the output will depend on S. Okay, so when R is 0, S is 0. Let's see what happens when R is 0, S is 0. When R is 0, this is R is 0 and S is 0. Then what happens is that suppose this Q was already at 1. Q was already at 1 and R is 0, S is 0. If Q is at 1, then the output of this NOR gate is 0. And since so this is the input, R is already 0, so the output is 1. The output is 1. So output is still. So if Q is 1, and R is 0, S is 0, Q will stay at 1. There is no change in value of Q. Similarly, if Q is 0 and R is 0, S is 0, you can see if Q is 0 here, R is 0, S is 0, this is 1. And if Q is, this is 1, if this is 1, then R is 0, this is 1, this is 0 again. So if Q is 0, it is 0 again. So Q, there is no change in value of Q. So if R is 0, S is 0, if Q is 1, it will stay 1. If Q is 0, it will stay 0. And Q bar, you can see, will always be the reverse in complement of Q. Okay. Now let's see if Q is 0 and R is 1, S is 0. Q is 0, R is 1, S is 0. If R is 1, the output will be 0 here. Okay, output will be 0 here. If and 0, 0 is, the output is 1 here. So the input of R will be 1. So if R is 0, so it is 1, 1. So the output is 0. If R is 0, Q will be set to 1. Whatever be the previous value, you can check for both previous value of Q to be 1 and 0. If R is 0, sorry, if R is 1 and S is 1, Q will be set to 1. If R is 0, S is 1, Q will be set to 0. Okay, so let us write this down as a truth table. Okay, let us write it down as a truth table. So we call this as set and reset. If the set and reset S and R are both 0, there is no change in the output. It is for data storage. When set is 1, reset is 0, Q is 1. Set is 0, reset is 1, Q is 0. 1, 1, you cannot set both S and R to 1, 1. It will lead to ambiguity. It's called an invalid state. We'll see why it's called an invalid state. It will lead to ambiguous output. It will lead to ambiguous output. We'll soon see why that is so. So you should not use the inputs S is 1 and R is 1. Other three inputs have the following truth table. Rather, I should not call it a truth table. It's rather called a state table, because it tells you what the next state will be depending on the value of S and R and the current state Q. Okay, and this is this is called a SR latch. This is the symbol for SR latch. You have two input. In fact, this will be if you use in NOR gate, it will be S bar, R bar, Q and Q bar. So this system is called a latch in the sense that you can hold the value for some time and you can write the value using your S and R input. This particular case is called a SR latch. Okay, so in general, latches are bistable multivibrator. They have two stable states and they can switch between them. And you can change the states by some triggers. The triggers can either be a label trigger. For example, in the SR latch, whenever I set the input to either a voltage level 0 or 1, whenever I set the input S and R to a voltage level 0 and 1, it causes a change in the output Q, a change in the state Q. So this is called a label triggered. It is called a label triggered latch. There is another type of latch which is called a clock triggered. That means it's not that whenever input changes, the output will change. There is an additional condition that is required, which is a clock, rather a clock edge. So whenever, so in a label triggered, whenever immediately in the sense that subject to the delays of the circuit, whenever there is a change in input, the output will change, Q will change, the state will change. In a clock triggered, the moment there is a change in input, the output may not change. It will wait till the next clock edge, either a up clock edge or a down clock edge. It will wait till the next clock edge, and then it will change. So this is called an event triggered or a clock triggered latch. And an additional criteria is required. This is useful for synchronization in the sense that in a label triggered, as and when the input changes, almost immediately it changes. But if there are multiple such memory elements, and if you want all of them to change at the same time, you need an additional event which occurs simultaneously for all these. Say I'm using k bits for all these k latches. The clock should happen in the same time. It should synchronize them, and the output should change only at the clock. A synchronous latch. Such synchronous latches are given a special name called flip-flops. Given a special name. So what we'll see that actually every label triggered or a label triggered latch can be augmented with a little bit of extra circuit to make it a clock triggered latch or a flip-flop. So every latch, so we'll call a label triggered latch as just a latch and a clock triggered latch as a flip-flop. So every latch has an equivalent flip-flop version with some additional circuit. Okay, so what we'll do is that we have studied one of the simplest latches, which is the SR latch, where the SR inputs change it. We'll see many, at least 3 more such latches and the corresponding flip-flops. We have seen the SR latch. We'll see the D latch. We'll see or the delay latch. We'll see the T latch or the toggle latch, and we'll see the most general form of latch, the JK latch, or more commonly the JK flip-flop, the Jack and King flip-flop. And we'll see their circuits, and we'll see that how to design their circuits. It is to be noted that it is always possible to convert one type of latch or a flip-flop to another type of latch or a flip-flop. There are other type of latches and flip-flops also. I'm talking about the most common 4th type. It's easy with some additional combinatorial circuit. You can convert one flip-flop to the another flip-flop. So whatever flip-flop you have at your disposal for building your circuit, if you need another type of flip-flop, you just use additional gates to convert it. Usually the most versatile flip-flop is the JK flip-flop, so that's most commonly used. So when we are analyzing this different type of flip-flops and latches, there are some 3 things actually we study. One is so the situation is like this. You have a standard, you have a output and you have some inputs. This can be S, this can be D, this can be T, this can be J, and you have 2 inputs, let's say, and often there is a clock. We'll see soon what is a clock. And whenever an input changes in the next following clock cycle, the output will change. So this change, depending on what input, what output is characterized in the following way. So one is what is called a excitation function or characteristics function. Characteristics function. This is given in the following way. This is either given as a truth table. I'm writing it down as a Carnot map. Okay, so these are my inputs, let's say S and R, and this is what I write is that I have this notation. Suppose Qt is my current output, and in the next clock it will change to Qt plus 1. So this I am writing out the on values when Qt plus 1 is 1, depending on the current value of Qt and the values of the input. So for example, SR, it might be something like, so let me write it, 0 0 0 1 1 0 1 1 1 0. So if I write down, say 1 1 doesn't happen, so this is a don't care. 1 1 is an invalid input, and S is 0. S is 0, and whatever Q2 is, output will be, it's not an onset. When S is 1, output will be 1. S is 1, output will be 1. And yes, anything else? When S is 0 0, then it is same as Qt. So if Qt is 0, it is 0. If Qt is 1, it is 1. And these are 0 zeros. These are 0 0. Because if R is 1, it is 0 0. And 1 1 is don't care, it's an invalid state. So this is the truth table. You can also write it down as a function. Say Qt plus 1 is what this will be. Let me see, it is R times Qt. Maybe I'm wrong, I have to check. Let's form the truth table. So this is one truth table, this is one block, and this is one block. So you can what it is, let's see. So this block means it's S, this is S, these blocks corresponds to S, and these blocks correspond to it is Qt is 1 and it is R bar. Okay, so this is the excitation function. You can also write it down as a state table, because see, fine, I have written it as a function Qt plus 1 as a function of input and Qt. I can also write it down as a state table. How do I write it down as a state table? I usually write the excitation table in this form. I write down Qt, I write down Qt plus 1. So these are all the transitions. So there can be 4 possible transitions. So 0 becomes 0 in the next state, 0 it becomes 1 in the next state, 1 it becomes 0 in the next state, 1 it becomes 1 in the next state. And what are the requirement of input? So this is the input requirement. Input requirement. Input requirement can be if it is 0 and goes to 0, it is again 0. It can mean the two condition. Input requirement can either be 0 0, sorry, yeah, 0 0, that is no change, or it can be reset equal to 1. Reset, if reset is 1, then also reset is 1, then also Qt plus 1 will be 0. Okay, so this is basically a don't care. So I have S equal to 0, this equal to don't care. How can 0 1 happen? By this. How can, because see, no change is not there, there is a change. So how can this happen? By this. How can this happen? How can 1 and still be 1? Either it is a no change, or S is 1, set is 1. So again, this is a don't care, this is don't care, and this is 0. Okay, so this is the excitation table of the SR latch. So these are equivalent actually. So this I have written it as excitation function, and this I have written as a excitation table. Okay. So this is for the SR latch. You can similarly do it for other latches also. Okay, so this we have already explained. This is the, in fact, this is not a truth table. This is actually an excitation table, I should call it. This is the excitation table for the NOR gate based SR latch. This is the working. I have already explained the different transitions, how they happen. Let us look at one thing. Let us look at the condition where let us look at the condition where the input is 1 1. In fact, I have slightly drawn it wrong. That this is actually Q bar. So if you write the other reflected way, I am just writing R on the top and S below. I slightly made a mistake in the. Okay, so suppose both are 1 1. So when I say that this is level triggered. So whenever an input 1 comes, output is supposed to be 0. This is the R input. Output is supposed to be 0, but with some delay. So if both of these NOR gates have the same delay, both of these have identical delay, then what will happen? So suppose initially, let's say it was 1 1. Let's say R and S are 1 1. Then in the next step, I apply 0 0 to it. I apply 0 0 to it. So it was initially 1 1. Then I apply 0 0. So what will happen? If it is 0 0, the previous state should repeat. So suppose this is 1 1, and if this is 1 1, let's say this is 1 1, and then 0 0 comes. The desired behavior should be when 0 0 comes, it should hold the previous state. But let's say what happened if these are both are equally, there is the same delay, then it will stay 1 1. You can easily check that it will if this is 1, this is a NOR gate, so this will be 0, and if this is already 1, let's say the output is already 1, it is already 1, so this will be 0, so 0 and 1, so this will stay the same. Okay, but suppose if one of the gate is slightly faster than the other, then what will happen? So if this gate is faster than this will first become, R is 1, this will first become 0, and once this is 0, this will become 1. So if this gate is faster, after you apply 0 0 followed by 1 0 0 after 1 1, this will become 0 1. Whereas if this gate is faster, you can easily check, this will become 1 0. So the output depends on, if we follow this input sequence 1 1 followed by 0 0, output will depend on which gate is faster. It will depend on the implementation. So this is an ambiguity. Since you don't know which gate is faster, it may lead to, you really don't know. There is an ambiguity in the output. This is called a race condition. Okay, so race condition may happen. That's why this input 1 1 is an invalid. This is not allowed. You can realize the SR latch also using NAND gate. The same excitation table. You can see here. So S goes to, you can easily check the same feedback circuit, the latch cross connection circuit, cross feedback circuit. same latch, you can easily check. The way to check this is that you can do it. I'm just stating how to do it. The way to do it is that assume this inputs. You assume some value of, you assume the inputs, let's say as 1, 1. You assume q equal to 1 first and see what happens. Then q equal to 0, see what happens. Because see, the output will depend on three things. It will depend on qt, it will depend on s, it will depend on r. So all possible combinations of s, r, q, you should check just using the logic gate formula what qt plus 1 should be. Okay, so in this case, again, I'm not going. You will see that this is the desired thing that you'll get. So you can realize it using a NAND gate also. So these latches, this SR latch, for example, has many advantages. One of the use is what is called a chatterless switch. So if you take any mechanical switch and you want to go from say 0 volt to, so this is two inputs S and R. They are connected to 5 volt. If the switch is in position 1, then S is 1, R is 0, R is grounded. And if we change the position, then S is 0, R is 1. These are grounded. So if you connect this, you will see even if so the mechanical switches usually they bounce between 1 and 2 state. Even if you turn it on for a small amount of time, they will bounce. Okay, so if you have this kind of latch element, what will happen that even if it bounces, it will hold the value. So the first time there is a contact, suppose you want to make S equal to 0, first time there is a contact, it will hold that value. So if your input waveform is like this, that one you see on the left, the output will not have this chatter. Again, this you can easily analyze. If you look at this diagram and choose the logic values to this NOR gate, you will see the output will hold on here. It will not chatter. Okay, so this is one of the use. Of course, there is a little bit delay of the time taken in the first transition, but in normal switch, the real transition will be this much. But this will be only this much, and in a much one order less time. Okay, so now so this was my basic SR latch, and NAND gate implementation of a basic SR latch. Now let's add some additional circuit to it, additional combinatorial circuit to it. So what we do is that instead of directly S and R values here, I get the, let me call it S prime R prime, I get them by the input NANDed with something called an enable input. I've written this is an enable input. So right now just forget about this clock, just assume that this is a logic input. I call it as E, enable input. So I have this symbol. So we have S input, I have R input, and we have a third input, which is the enable input. And you have two outputs, Q, Q bar. You can easily see that do I have a transition? No. You can easily see the transition diagram will be, transition table or the excitation table will be like this. What was the excitation table earlier? It was S, R, Qt plus 1. So when S is 0, R is 0, Qt plus 1 is Qt itself. When S is 1, R is 0, it is 1. When S is 0, R is 1, it is 0. And this is invalid. This is invalid. This was the normal SR latch. So what we do, I add an additional input called the enable input. And I do in the following manner. Only when the enable input is 1, these actions will take place. This again you can easily check from this circuit. You can easily. Only when the enable input is 1, these actions will take place. So on 0 0 input it will take this also. On 0 0 input it will hold it. On 1 0 input it will set it, and 0 1 it will reset it. Okay. Only when enable is 1, the output, these actions will hold. When the enable is 0, whatever be your S and R, it will, no change in output will happen. It will hold the output. Okay, it will hold output. No change in output will happen. Only the latch is kind of activated or open only when enable is on. Only then the latch is active. When the enable is 0, latch is inactive. It just holds the value whatever input you give. Okay, so this is sometimes called a gated latch or a enabled latch. Just with the help of a combinatorial circuit, you are adding a third input. You are adding a third input. You can also easily draw the transition diagram and the excitation table for this. Okay, so now what I can do is that this enable input I can give as it an train of pulses called a clock pulses. I can give it a train of pulses. What is a train of pulses? It is a signal which is staying on for certain time, again becoming 0, and it is doing this periodically with a regular frequency, regular time period. It's getting this input. Okay, it's on for some time called a T on time, and off for some time called a T off time, and T on and T off are continuous, always same. Such an input, such an enable input would be called a clock. Now, what is the advantage of this? Now you see your S and R, they can change at their own will, depending on what type of external inputs you get. They can change. They can be something like this. But only when the clock is on, the clock is high, at that moment of time, whatever is the value of S and R will affect the output, and the output will change only during this period. The output can change only during this period. Okay, the output can change only in this period, and it will make a change depending on what the value of S and R were at these instances. Okay. So enable, you remember I told that only when enable is on, the latch is kind of active. It responds to the input. When the enable is off, it just holds the value. It doesn't respond to input. That's easy to realize actually. You just have these two additional NAND gates, you can realize it. You can easily check out. It's just a combinatorial circuit. Okay, so the advantage of this enable input of this additional gate is that I can now force the output to change only at the on period of the clock. Only then it will change. Input, it may vary or something, but it will change only then. What is the advantage? The advantage is that this provides a synchronization. This provides a synchronization, because if you have multiple such latches, and you have input, and maybe there is a cascade of latch, maybe the output of one latch goes to the input of the other latch. So the input, moment there is a cascade, to the second latch will get an input slightly later than the first latch. The 100th latch will get the input significantly later than the first latch. So their inputs may come at different time. The inputs may come at different time, and accordingly the outputs may change at different time. That's not desirable. what we say is that this clock train of pulses that we have, these are common across all these different latches. These are shared. These are common across all these latches. So all these latches see the enable input at exactly the same time. Exactly means subject to this delay of a single NAND gate. Subject to delay of the single NAND gate, a small nanosecond kind of delay on the single. But except for that small delay, they are all going to have the clock pulse high at the same time, which means that they are going to respond to the input, and so their outputs are also going to be changing only at that same time, and they will respond to the value of the input also in the same time. All of them will respond to the value of the input at that snapshot in time at which the high of the clock pulse happens, at the snapshot in time. So there is a notion of time, there is a timekeeping, there is a clock. At that moment of time, whatever is the input across all the latches, that input will be considered, and the output will change also only in this time. Okay. All right. So that's the benefit, that's the synchronization we get by having this enabling input. Okay. So now, how much do I keep the width of this clock pulse, the on time? How much we keep the on time? Okay. How much we so the clock, as I said, is any periodic signal that keeps time. So you have an on period and you have a total period. So then the duty cycle is T on by T period. So what we want is that this clock pulse should be very thin, because what we usually want is that only one output change, only one single output change will happen, because see, as long as the clock is on, it is enabled, the latches are open, the latches are activated only when the clock is on. So latches are open in that means in that period, whatever change in input is there, it will be reflected in the output. If there is a change in input, there will be reflected in the output. What we want is that in one clock pulse, only one transition should happen. Just one single transition should happen. Okay. So but I have no control. When the clock is on, whenever input changes, output changes. So input changes 5 times, output also changes 5 times. So what we do is that we take the clock pulse to be thin enough so that only one single input change happens. One single input change happens, which means that only one single output change happens. Okay, so this is kind of if we call this change as in computation, one single computation operation. One single operation, computational operation, happens in one cycle of the clock. One instruction is executed in one cycle. One operation happens in one cycle. But can we make it infinitesimally small, just one single spike? Can we make it? No, that also we cannot make it, because see, these gates will have some delay. These gates will have some delay. So whatever S and R value you give, the time they travel, they come as input to the latch, there will be some delay. So if the clock pulse width is smaller than that delay, by the time the signal reaches the latch, the clock has already become 0. So the latch is deactivated. So I should keep the latch on for an amount of time which allows for the delay in a single gate, That much. So the clock width should be more than the delay of a single gate, so that it has a tolerance, it allows this time to change the output, but it should not be staying on longer than that, because I want only one operation per clock cycle. And that's done. I'll wait for the next clock cycle. Okay, I'll synchronize. I'll wait for the next clock cycle for synchronization. Make a change. Okay. So all you see that what is the clock speed of a CPU and all this. This is controlled by this factor. I want the clock. Of course, there are other considerations like power and all those things, which are the main contributions for the moment for the modern chips. But the higher you take a clock frequency, okay, so you see there's a constant that T on should be less than T period, and you have a lower limit on T on. So you have a lower limit on T period also. So ideally you want T period to be very high so that you make the transitions very fast, but you cannot make it arbitrarily. You want T period to be very small so that you want a lot of computations in small amount of time, but you cannot make it arbitrarily small because the gates have a delay. Okay. All right. So this is clear. This is a gated latch, gated SR latch. This gated SR latch, I'll be calling it as a SR flip-flop. I'll be calling it as a SR flip-flop with this transition excitation table. Now you see that this basic SR flip-flop, I can again add some additional features to convert it into other behavior that I might require. So let's see if I have this S and R, and I have the clock, and along with the clock I added T input. Okay, sometimes call it trigger or a toggle input. Okay, so what this toggle input does, again, I'm just writing down the excitation table. You can actually verify also the excitation table by checking these inputs. All right, so let's check the table. So the circuit is QT is 0, QT plus 1 also wants to be 0. I should keep the toggle at 0. If it is 1 1, I should also keep the toggle at 1. I want to flip the output state. I want to toggle the output state. I should keep the toggle input as 1. I should turn the toggle input 1. So the effect of turning T equal to, so what happens is that moment T is 1, this toggles. Okay, and as long as T is 0, it continues in the same state. Okay, so this can be easily achieved using a basic SR latch with this additional AND gate with the clock. Of course, the changes will happen in the clock, and you can this, if you see, it's very easy. So the output is just the XOR of the toggle with the current output. Okay, I'm written Y here, but okay, I think this Y is actually QT. Okay, now let us look at another conversion of this basic. So by the way, so I'm using the basic SR latch with some additional circuit. You can sometimes you can actually realize these transition excitation functions by a circuit, by a feedback. So that basic latch circuit, cross coupling circuit, that has to be always there. But what gate you choose, what other circuit you choose, you may have a simpler realization than using a SR latch of this transition table. But okay, I'm explaining it using this. All right. Now let us look at another modification. See, one of the limitation of this SR latch was that this 0 0, this case, let's see, this 1 1 was an invalid state. This 1 1 was an invalid state. So basically I have only 3 things to control, 3 input combinations to control. But to have more power, I should have this 4th combination also. Okay, so why not make this thing? They have a latch which is like this. 0 0 is no change. Set 1 is output set 1. Set 0 is output set 0, and 1 1 is a toggle of Qt. Why not do like this? So 0 0 is no change. 1 1 is toggle of the output. Okay, 1 1 is flip of the output. This is called a JK latch. So this is the excitation table. You want to change from 0 to 0. We'll see this excitation table. So basically, what we want is the let's write this down. So how can you be from 0 to 0? Either you have a no change. So this can be J can be either 0 0, or you have a reset to 0. So this can be K. So K is like a reset. This can be 1. So this becomes a don't care. Similarly, 0 to 1 you make a transition. Either you make JK 1 1, which is a toggle input, or you make J equal to 1. Okay, J equal to 1 and this equal to 0. It doesn't matter what this is 0. So this is don't care 1 0. Similarly, for this. Okay, let's see the realization. Maybe I should first show you the realization. So again, I am realizing it is a basic SR clocked SR latch. We'll let us see that you can realize, you can directly write down the realization in terms of gates. All right, so you take the SR. What you do, the output of S, you have 2 additional AND gates, and you have a clock, you have AND gates. AND gate, one of the input is J and K. The J actually, the S got converted to J, and the R got converted to K. But there is a feedback. Okay, so you can see that actually here there is a nested feedback. So within this SR latch there is a feedback, and the entire thing is again feedback. So there is a nested kind of feedback. Okay, so now so the idea is following. What I actually want to do is that if I set JK to be 0 0, output should hold, should be the same as Qt. Qt plus 1 is same as Q2. If JK is 1 1, Qt plus 1 is bar of Qt, it toggles. If J is 1, K is 0, output is set to 1. If J is 0, K is 1, output is set to 0. Okay, that's what I want. And again, I am maybe not doing this. You can check it out from this circuit, and that is exactly what will happen. Given the excitation table of the SR latch, add this additional AND circuit, you get this new excitation table. Again, you can check it. Okay, so I think you should check it. I think you should check it. Okay, so the output can be 1 in 2 ways. Either in the previous state it was 1 by virtue of no change, or it has been set to 1. So that means one of these J and K becomes a don't care. So if there is a transition from 0 to 1, K becomes a don't care, J becomes 1. Similarly, if there is a transition from 1 to 1, J is a don't care, K is 0. Similarly, if the output is 0, there is a transition from 0 0, it is 0 don't care, 1 to 0, it is don't care 1 for J and K. Okay, so this is kind of much more versatile. So one exercise that you can probably do is to draw something called a timing diagram. Okay, it's kind of a use case analysis. So this is my clock. This is, let's say, a train coming like this. And this is, let's say, my J, which can be anything. And this is my K, which again can be anything. And I want to write down my output. Okay, I want to write down my output. Note that this is a clock enabled. That means only when the clock is in on state, any change will be reflected. So let's do the analysis. So here clock is 0. So whatever is the value of Q, it will still, let's say Q starts with 0. So it will till this Q will state 0. Say initially Q starts with 0. I could have done it for Q starting with 1 also. So now during this period, what happens? J is 0. So in fact, this is an undesirable. Okay, J is 0. K has moved from 0 to 1. So J is 0. K has moved from 0 to 1. Q was already 0. So what will be the output? What will be the new output? Anybody? J is 0. K is 1. J is 0. K is 1. What will be the new output? J is 0. K is 1. The output is 0. In both cases, the output is 0. So Q will be 0. Q will be 0 till the next clock. Till the next clock, Q will be 0. Now, if this is on, Q is on. Now, J is 1. So this is somewhere here. J is 1, K is still 1. Okay, so J is 1, K is still 1. So now what will happen? Anybody? J is 1, K is still 1. And Q is already 0. So Q is 0, J is 1. So it will transition to 1. It will transition to 1. So it will transition to 1 here till the next clock cycle. All right, in the next clock cycle, what happens? J is 1, K falls back to 0, and Q is 1. Q is 1, J is 1, K falls back to 0, so it will stay 1. It will stay 1. So this will not fall, this will stay 1 till the next clock cycle. What happens in the next clock cycle? J is 1, K is 1, J is 1, and Q is already 1. Okay, J is 1, K is 1. So it will be falling back to 0. Okay, so this way you can draw the timing diagram. All right, so there is one more small change you can make in the SR latch or the JK latch that we have discussed. Instead of having two inputs J and K, I can actually tie the inputs. So J is, and that input, single input I call D. So J is D and K is D bar. I add a NOT gate here. I add a NOT gate here. Okay. So if you do this, you will see that you get a very simple excitation function, characteristics function. The yt plus 1 will be same as what is the value of dt. So the timing diagram will be very simple. Whenever in the at a particular clock cycle, whatever is the value of dt, that will be the value of yt plus 1. Okay, that will be the value of yt plus 1. Right. So this is sometimes called a data latch or a delay latch. You just have one input, and again here you can draw the transition, the excitation table, and so on. But it's one of the simplest. It's easy. The excitation function is an identity kind of thing. It's same as itself. Okay, so this is what we have discussed. You have to keep the thing. Now, so 3 types we have already studied. 3 types. Yes, 3 types. So the SR, the T, the D, and the JK. 4 types we have studied. 4 types of latches we have studied. And we have also studied a clock enabled latch. That means the timing diagram will change only at the clocks, only when the clock is on. So just think about this carefully. So only when the clock is on, these changes are happening. And each of these 4 types, the D, T, SR, and JK, you have, I think you have fairly understood there. Let me summarize it quickly. So SR is so let me call this as input. When input is 0, 0, output is no change. When input is 1, 0, output is 1, 0, 1, 1, 1, 1 is invalid. You have JK. When input is 0, 0, again no change. When input is 1, 0, it is 1, 0, 1, sorry, 0, 1, 1, it's toggle of the current. Let me call it toggle. Current toggle of the current state. D is very simple. You have only one input. So if input is 0, output is 0. If input is 1, output is 1. You have T, which is if input is 0, it's no change. If input is 1, it's toggle. Okay, so JK is kind of a more extension of SR, more versatile version of SR, with the 4th input allowed, a toggle input allowed. And D and T are kind of reduced version of SR and JK. They have only one input, the other input is tied to this input. And D is directly, whatever is the input is transferred to the output in the next step. And toggle is, if the input is 1, the output is toggled. So these are the, and I think you can easily, I'm not doing it, you can easily write down the excitation table for all this. And once you write down the excitation table, you can also write down the characteristics equation of the excitation function. How is Qt plus 1? So the excitation table, let me again write it. Excitation table is this thing, that Qt plus 1, these are the transitions, and these are the input requirements, say SR or JK, whatever you take, or even D, if you have single D or T, whatever, these are called the input requirements. So you take all possible transitions, and what are the input requirements for this? So for example, this transition is for SR is 0, 0, and this is 0, don't care, and so on. So you can write down. So we have already written down some of this required values of J and K. So from this logic, you can write down. Similarly, you have a excitation function or a characteristics equation which is you write Qt plus 1 as a function of Qt and the inputs. Let's say J and K are the inputs. Okay, so this can be either as an expression, say J times j and qt plus k bar qt. This can be either as an expression or it can be as a Carnot map. Okay, so you have jk values and qt plus 1 values. You have some onset, and you have sometimes you may don't care also. So this is just a expression for this. Okay, so for this fourth type of latches, or I should, since I have a clock already, I should call it a flip flop. We can draw this. Again, one more thing you should not forget is that the flip flops are enabled or activated only when the clock is high, clock is on, only when the clock is on. So that means basically what you should do is to synchronize everything so that only when clock, so you should have a small thin clock pulse and only then changes happen. Ideally, we want the clock pulse to be thin enough so that only one change happens. It is not sensitive to change within that clock pulse, only one change happens in a clock pulse, and the clock pulse is wide enough to allow for that change. It should, the input, the combinatorial circuit delay should be less than that change. It should take into account the delay. Okay, but then this gives us a problem, because you really, so the width of the clock pulse now becomes dependent on the delay of the circuit. You should choose the clock pulse width should be determined by the delay, and you really don't know the delay. If you cascade gates, the delay will be more and so on. So, and you don't know which circuit you are using, which kind of logic you are using, CMOS or what you are using. So it depends on that. So to solve this problem, you have something called an edge triggered. In fact, you have two methodologies. You have something called a edge triggered. So you do what you do is that to account for this problem with the timing, you use some additional circuit so that this ambiguity goes away. This ambiguity goes away. There are two strategies actually. One is called a edge detection. And another is called a master-slave combination. Solve the timing problem. Pulse width problem. Okay. So what I will do is the following. Let's take the flip-flop. So by the way, this is the symbol of the flip-flop. This is called a clock. So what I will do is that, in fact, this is not the clock. This additional wedge is there. I'll tell you what this means. This means that if you look at the timing diagram, this latch is enabled or this latch is activated only in the up edge. Only in the up edge of the clock. So earlier I said whenever the clock is on, the flip-flop stays enabled. Now I say different. The so these are the enabled period, or the activated period. These are the activated periods. And this, I want this to be rather small, but I don't know how small it should be. It cannot be too small. Instead, what I do is that I say that the activation period of the latch is not the entire on period of the clock. It is only in the edge of the clock. So I can now have a clock like this. I don't bother about a small clock pulse width, but the changes will only happen in the up edge or the down edge. Okay, so the latch can change, will consider the input, whatever is the value of this input in this time, in this snapshot of time. And the output also will change only at these events. only at these events. What is this event? Up edge event. Okay, sometimes called a leading edge event. Only at this leading edge event, only the event. What is the event? Event is clock going up. Only that moment of time. What is the value of this input j and k? At the instant of time where this up edge event happens, they will also be considered. So it really doesn't matter what happens to the value of j and k here or here or here or here. Only the value sharply at these points matter. And the output also will be transitioned only at this, subject to again delay of the gates. On that much delay of a single gate is not much. Only at these points the output will change. Only at this point. So the output is, if you look at the output, the change, whatever it is, will be only here. It may stay constant depending on the logic, but the change is only here. Okay, so the timing, in the timing diagram, if you see the timing diagram of the output, the input is free. Input is the external input. It can be whatever it is, but the output is always flat. And the output is constant from edge to edge, from edge to edge, leading edge to leading edge. It is constant. Okay, of course, again, I mean, if we look really fine, this leading edge is actually a small period because this clock will is something like this. So this leading edge is actually this small period of time, but that's much small compared to the width of the pulse. Okay. By the way, usually these clocks are kind of, they are not realized by CMOS, and these are kind of quad circuits or vibrator circuits, which due to their physics, they keep on vibrating that way. So this has again a lot of advantage because all this delay, pulse width, all this we need not worry about. And only at this edge. So what I can do, so moment if I have this edge, what actually is done in practice and what I will do is that I will take all these flip-flops, the JK flip-flop or the SR flip-flop or whatever, and their enabling input, earlier I was saying is on off clock, now the enabling input is on only at this leading edge. This is the only period in which it is on. So if we look at the enable input, it changes, it's only this much. And how do you know it's the leading edge? I'll show you. We'll have some additional circuit known as edge detection circuit. Edge detection circuit. So there will actually be an edge detection circuit. There will be a normal clock coming here. The edge it will go through the edge detection circuit. It will detect the edges, and the edges will be actually the enabling input. Edges will be the enabling input. Okay. And the remaining excitation table and the characteristics table, they remain the same as the JK flip-flop, except for this edge except for this edge triggering circuit. The remaining of the circuit is exactly the same as before. The gated JK latch with the enable input. It's exactly the same. And again, if you forget the enable input also, it's again the simple excitation circuit. So this will repeat depending on enable. This is the JK table. So this is for, so this entire thing is for enable. If enable is 0, it's just the previous state, and enable again is the output edge detection circuit. So this kind of edge triggered flip-flops are denoted by this kind of wedge. This is the symbol for a positive edge triggered flip-flop. If you have a small bubble here, it's called a negative edge triggered. It's the symbol for a negative edge triggered flip-flop. That means the transitions will happen at the negative edges, down edges, or the trailing edges. Okay, and rest is same. There is another way you can solve this problem. is by something called a master slave configuration. It's called a master slave configuration. So let me explain what this master slave configuration is. So whatever flip flop we check, the JK or SR, it doesn't matter. So this is any flip flop, a JK flip flop or a SR flip flop or whatever. We have two such flip flops blocks. One we call as a master block and one we call as a slave block. Okay, master block and a slave block. So the input of the master block is the external input. Okay, and there is kind of a feedback from the master block to the slave block, and this input actually also goes here, and then finally you have the output Q bar. But the clock that we have, note that I'm not using a edge triggered block, maybe, or I can also use a edge triggered block if you want. So the clock is kind of a common between this master and slave, except for a NOT gate added in between. So you have a common clock. So this clock for this master block, and this is the clock for the slave block. Only thing, there is a NOT gate, there is a bar operation in between. Okay. So what is the advantage? If we look at the clock for the as an enabler, so this JK, the master JK, when the clock is on, only then changes will be there. Let's say this is the same. So this is the clock is on period. This is the clock is on period. Only then whatever change in the output. Let's say this is the output only. Those kind of changes happen. Now, if we look at the slave, you see that two things happen in the slave. First thing is that the slave is a reverse of this clock. So it will be because of this NOT. It is the reverse of this clock, but not exactly reverse, not point by point reverse. Why? Because this NOT gate introduces a delay, a small delay. So this slave's clock, rather the slave's enabling input, is complement of the master's enabling input, but with a small delay because of this NOT gate. If we call it delta, so there is a small delta. So there will be a small delay here. Similarly, there will be a small delay here. Similarly, there will be a small delay here, and so on. Okay. So now you see this output of the master block is input. So this changes only when this is on. And this changes when this is on and clock is enabled, but clock is complement of this. So it is only during this thin period, only when master's output change, because master's output clock was on, master's clock was on, it changes. And the slave's clock is supposed to disable, but it delayed it a little bit because of this NOT gate, it delayed it. So only in this small block, both conditions are met. Master is changing, slave is not yet disabled. Slave is not yet disabled and master is changing. So in effect, you get a small, if you look at the second slave block, whose output we are seeing, you will get something like this. We'll get something like this, which is again the small pulse which we wanted to have earlier. It's a small pulse we wanted to have earlier. Okay. All right. So, so it's kind of, you can also think it of like this. So the master's master latches output get transferred to the slave latches output, and the master is so when your clock is 0, when your clock is, so if we look at the clock, there are three things that are happening in the clock. One is the clock is staying at 0. One is the clock is staying at 1. So this is clock equal to 0. This is clock is staying at 1. And this is clock, and this is clock 1 to 0. In this event is clock 1 to 0. Okay, so let's see what, sorry, this is clock 1, this is clock 0, and this is clock 1 to 0. This is also an event 0 to 1. So let's see what happens. When clock is 0, the master is held. Master is held, and master's output is transferred to slave's output, slave's input. Master's output is transferred to slave's input. When clock is 1, the slave's output do not change. The slave's output do not change. Okay, so slave's output only when the clock goes from 1 to 0, a trailing edge, then these inputs are enabled. So then you have the usual combination. You have the usual combination. So JK01 is 0, JK10 is 1, JK10 is 1. Doesn't so these are set reset, so it doesn't matter. 1 1, and it is a toggle. 1 1 is a toggle. 1 1 0 is also a toggle. 0 0 is no change. 0 0 is no change. Okay, so this is what we achieve by a master slave flip flop. There is one more additional circuit that is also some. So I have talked about I have not yet talked about the edge detection. I have talked about the master slave. There is one more circuit that is sometimes provided with a flip flop. It's called a asynchronous preset clear. Because you see, in a clocked flip flop, the changes will happen only at the clock edges. But sometimes what you want, maybe in the beginning of the operation of your flip flop, or sometime in between due to interrupt or something, irrespective of what the clock value is, I want to either preset the output to 1, or clear it to 0. Okay, so this is kind of a overriding input. See, so the clock is there, and the edge of the clock, something is happening synchronously. But sometimes I want some asynchronous intervention due to interrupt or something. So then this preset and clear. So this preset and clear, what it does, if you set preset to be 1, whatever is the clock state, input state of the latches and so on, output is immediately 1 asynchronously. Don't wait for the next clock cycle, and similarly clear makes it 0. So this is an example of a D flip flop circuit with this preset and clear input. As you can see, what happens here is that the latches have a third input, which is the preset clear. Earlier there are clock and D, or clock and JK or D, because I've tied J and K, tied S and R. So, but you have a third input to the latches. Okay, third input to the latches, which is the preset and clear. And then that will, again, this, if you analyze the excitation table and the excitation equation, you will see that this preset doesn't depend on the clock, it can do it. You can also have a synchronous preset clear. That means it will preset and clear. It will preset and clear, but only at the clock edges. Only at the clock edges it will preset and clear. Okay, so the asynchronous was anytime it can preset and clear. So what your output is, this is your clock. Your output is, let's say if it is a trailing edge, is doing something, and you get a preset here, you get a clear here, immediately it becomes 0. What will happen in synchronous is that it will wait for the next leading edge, trailing edge, and then it will become 0. Again, this circuit you can analyze. It's actually simpler than the asynchronous preset clear. You have input preset clear only to the first latch, not the second latch. But you can again analyze this. I'm not analyzing. You can get this behavior. So actually, I think it's easy. I am not doing it, but with the hope that you will be doing it. It is easy. See, all you need to do to write down the excitation table is to consider different conditions. So as I have said, that all you need to do is to consider these different combinations. Consider this different combination, or rather this different combination. You assume value of the inputs, you assume value of QT, and each of these you see what the output will be. Now this again has to be done in 2 steps. First step is that you assume the QT is 1, and then you assume QT is 0 in each of these 2 steps. So basically you take 8 different combinations. The value of the 2 inputs, in case of JK and SR, in D and T it will be 1 input, and the value of the current output. So in any of these circuits, if you go through the entries of these Q, J, K values, the excitation function, you will be able to find out what Q is. Just by the logic of the circuit, you will be able to find out. Okay. The key point is whenever you are assuming, whenever you are analyzing, suppose I give you some latch or something like this with some input, you basically do the same thing that you did in a truth table. Same thing that you did in a truth table. You enumerate all possible combination of input. Only difference is in the truth combinatorial circuit, the truth table consists of combinations of inputs only. Now you should consider the current state also as an input, Q also as an input, because it is a sequential circuit. Okay, so you take the truth table, all possible combination of inputs and the current state Q. You take all possible combination, and on them just apply this logic. Just apply this logic to find out what QT plus 1 should be. What QT plus 1 should be. Just apply this logic. The only, the important part of this logic is that there is a feedback loop. So you have 2 input to this S and R blocks. One of the input is external input. The other input is the current output. So in sequential circuit, the current output is also considered as an input. So because of this feedback, the current output is also an input. And then it's simple. It's simple combinatorial analysis, combinational analysis. Okay, maybe I'll just come back to this time. I'll just talk a little bit about this edge-triggered flip-flops, this edge detection circuit. So what this edge detection circuit does is that there are actually 3 latches. In normal JKSR or the master slave, you have seen that there are 2 latches. There are 2 latches. There are kind of these 2 latches. You can see 2 latches. Here also there are 2 latches in this master slave. What this edge triggering does, it needs 3 latches. Okay, it needs 3 latches. One of the latch is the kind of output latch. And these 2 latch are kind of differential latch because they are tied to the S and R input. They kind of are called, they are kind of differential latches. So the first latch kind of holds on, it sets in the positive, the enabling happens only in the positive. The second latch, the enabling is kind of the reverse, so enabling happens in the negative, in the other part. rather I should say it like this: the enabling doesn't happen in the other part, but since it is tied to the R input, its effect is its other part, and we have the additional D input. This is a D flip flop, so we have the additional D input. And because of this set reset mechanism, so this top latch tries to set it in this part, the bottom latch tries to reset it in the same part. So what it happens is the only reason, only time span where both set and reset agree with each other is in the edge. Okay, so you can sort of, I'll come to the detail. You can think of it like this: the top latch tries to set this output latch here in the on part of the clock. The bottom latch, of course, depending on the value of t, whether it will hold the value or not, tries to reset it again in the positive part, in the on part of the clock. Okay, so in the on part, both of them are trying to set and reset, set and reset. So it's only in this edge that they agree, and a transition can take place. And that's how edge triggering is done. Of course, the actual circuit, I mean, this is just a hand waving, I said. The actual circuit is a little more complex. You can actually analyze it. You can actually, this S and R are called the differential S and R. So it's S delta and R delta. These are the differentials. This is the clock. This is the D input. This is sometimes called the A input, and this is the B input, and these are the outputs. So if you analyze this latch, again, simple technique, inputs and current Q. If you take, you will see this is kind of the diagram. So S delta, the differential S, is CA prime. Is CA prime. And A, if you replace by substitute this, you will see that this is what it becomes. Okay, and similarly R delta is this is what it becomes. And as long as clock is 0 and RR and SS 1, output latch retains its older value. When clock changes from 0 to 1, and then RNS is as follows: if D is 0, Q is 0, this is the usual operation of the D flip flop, Q is 1. So that's what happened. Thereafter, RNS remains stable while C equal to 1, clock is 1, irrespective of changes in the T. Okay, and by this particular circuit, the R equal to S equal to 0 state is not reached. If it ever becomes that, it immediately changes to R1 S0. So again, this is the transition table that you can see. So you can, well, I mean, maybe you should follow these steps and see what happens. You'll of course get the same transition table. You can similarly have a negative edge triggered flip flop, D flip flop. Okay, so this can happen. All right, so I'll just end with one particular thing called a timing analysis. So this delay and all these things. So this is sometimes called the residual problem. This happens due to the delay in the gates. Okay, so if D is, let's consider a D flip flop. If D is 0 and clock is 1, and if D is initially, let's say D is 0, clock is 1. Suppose D becomes 1 when clock changes to 0, but before this delay delay has been taken care of. Okay, then the master latch, if you look at this master slave combination, any master slave D flip flop combination, it will come to an invalid state. Okay, so now what happens is that before another valid input comes, the master latch changes. All the gates of the master latch, the next gate they change. Okay, and then again the slave latch has an invalid combination. So this can happen. This is sometimes called a catch 0 or catch 1 condition. If somehow this 0 0 or 1 1 comes, they can catch it. They'll stay there, and this becomes output becomes in ambiguous. So there is to taken care of these delays and all these things, you have to do some timing analysis. There are two times that are important. One is the setup time. Setup time is the clock becomes 1, but it has to stay 1 for a certain amount of setup time before it affects for that much amount of time the data should be stable so that the latches get the correct output. If the data is not stable for this much amount of time, then the output may be indeterminate. Okay, so here is an example. You have two D latches, D1 and D2, and there is some combinatorial circuit in between connecting these two latches, and they have a delay, and the clock is synchronized, but the clock has some insertion delay. So the time available for D2 to reach D1 after the active clock cycle should be T clock. Within this time it should reach. Okay, within this time it will T clock, but T skew is a small time delay due to the clock with the skew and the setup time. Okay, and similarly there is a feedback. So sorry, there is no feedback here. There are two latches. D1, the time required from D1 to D2 after an active clock cycle is T C2Q. T C2Q. This delay in this latches from clock to Q is the setup delay, setup time. And as a result, you have a constant that this should be this is the time. The first one is the time available. Within this time, D2 should reach D1, and the second one is time needed. This time is required to transform, and naturally the time needed should be less than the time available. So you have this constant. So whenever you design these circuits, and the circuits will have a setup time which is C2Q, then a combinatorial delay, then a time period of the clock, then a skew time period, and a setup time. So all these constants should be satisfied for determinate operation. Similarly, there is a hold time. This is on the trailing edge, that means 1 to 0 edge. So after the active clock edge, this is the amount of time for which it should hold for stable output variation. Similarly, the same analysis you can do here. It's T C2Q plus the combinatorial delay, and the time required. It is the minimum time required to reach, and the minimum time for it has to stay. This T skew plus T hold. Again, this constant is there. So when you are actually building these circuits, you should, and you are using a lot of combinatorial circuit, these constants, this hold time and setup time in the clock, this should hold for the circuit to behave properly. Okay, so with this I kind of end this. Next class we'll go into design of more complex circuits. So we have studied basic latches, 4 types. Then with a enabling input we have studied, which we put a clock. It's a clocked latch, which we call as a flip-flop. We can have further circuits to surpass the problems of the stability and multiple changes in a enabling clock cycle by having either edge triggering or master-slave combination. We have seen their combination, and whatever all these circuits, you can analyze them either by the excitation table or the excitation function, and you can find out their operation. Okay, so this is the basic case. Finally, all flip-flops can be converted to other type of flip-flop by additional gates. Okay, so with this, we end our discussion on latches and flip-flops. In the next class, we'll use these latches and flip-flops to build some sequential circuits called counters and registers. Thank you.